Assalamualaikum warahmatullahi wabarakatuh. We will present our project, Electronic Leaf Controller System. Our group consists of Basili Abdullah, Mikhail Adam Rias, Muhammad Afif Asfar, and Ahnaf bin Zaizan. For this project, our project presenting the design and simulation of a digital elevator controller for an 8-story hotel from levels 0 to level 7. The system uses a 3-bit synchronous up and down counter implemented with JK flip-flops to track elevator floor positions. Elevator operation is permitted only when safety conditions are satisfied, including valid passcode entry, weight detection, card authentication, and closed doors. The controller was developed and tested using DITS software, applying essential digital logic concepts such as state machines, excitation tables, Karnaugh maps or K-maps, and Boolean simplification. This project demonstrates the practical application of digital logic theory in developing efficient and reliable event-driven control systems. Our combinational circuits uses basic gates, input switch, and 4-bit adders. And for sequential circuit, it uses JK flip-flop and clock enabler. And we put special features, which is weight limit detector, 3-digit password, and up and down switch. So for problem statement, the initial system used a 2-bit flip-flop counter, limiting elevator operation to 4 floors from level 0 to level 3 only, and to support a more realistic 8-story building, which is from level 0 to level 7. The controller required significant expansion and redesign. This included extending the counter to 3 bits, replacing D flip-flops with JK flip-flops, and redesigning the excitation and transition logic using Karnaugh map optimization. Additional enhancements involve implementing directional control for upward and downward movement, integrating security features such as passcode verification, door status checking, and floor validation, as well as implementing a weight limit safety mechanism to ensure reliable and secure elevator operation.
For suggested solution, a synchronous saturated state machine using 3 JK flip-flops is used to track the lift floor. The input X controls direction, 0 is equal to down and 1 is equal to up. The counter stays at 000 and 111 at the limits. Appropriate steps were used to design the circuit in DITS. So firstly, we made a state diagram which shows all the states for our lift. 000 is the ground floor and 111 is the max floor. When X is equal to 0, the state will move upwards. And when X is equal to 1, the states will move downwards. And for the second step, we constructed a JK flip-flop net state table, which shows the behavior of J and K from the net state of our output. The third step, we constructed our circuit excitation table by referring to our JK flip-flop net state table. We determine the value of J0, K0, J1, K1, J2, and K2 by referring to our present state and net state of Q0, Q1, and Q2. And then we implement the JK flip-flop net state table to get these variables. For the fourth step, we constructed our Karnaugh map from the circuit excitation table. And from this Karnaugh map, we are able to make our Boolean expression, which is our final step to creating our circuit. These are the Boolean expression for each of our variables from K0, J0, K1, J1, K2, and J2. System implementation. The elevator control system has designed and simulated using the Digital Electronic Education and Design Suites, which is DITS. It's control an elevator serving an 8-floor building, level 0 to 7, using a 3-bit synchronized up or down counter implemented with JK flip-flop to track floor positions. All flip-flops operate synchronously under a common clock signal. The system integrates conventional logic gates and or NOT, XNOR, and NAND to generate the required J and K inputs with logic equation derived using excitation tables and Karnaugh map minimization. Control inputs including passcode verification, weight limit detection, and direction signal, ensuring secure and safe elevator operation. A 4-bit passcode input, the leaf will not move if it does not input the right code, which is 69E. Await detection, the leaf does not move if it's over the limit, which is 3 tons. The direction of input X. X, if it's equal to 0, is count up, which is it's going up, or X equals to 1, which is going down. So how the system behavior and working logic? The system first verifies all safety and access conditions, including door closure, correct passcode entry, acceptable weight limit, and a valid target flow. Based on the target flow, the direction input determines upward or downwards movement. Once validated, all 3 flip-flops operate synchronously to ensure smooth state transition. The 3 bits counter then advances from the current flow to the selected target flow.
In conclusion, this project designed and simulated a secure password-based elevator control system using DIT software. The system integrates conventional and sequential logic to enhance operational security and reliability. While effective, it is limited by a fixed password and a preset rate limit, with future improvement including dynamic authentication and adaptive safety measures. That's all from us. Thank you.